Okay, this time we're gonna end up the strain engineering and why you use the high K material in the gate. First, the last time we gonna talk about the how work in the strain engineering that we use the atoms we use the difference atom structure to the combine to the SI, so we control the tensile or compressive strain stress. So a lot of it make us to control the semiconductors electronic characteristic because we use the strain engineering, the semiconductor is getting to scaling down and it makes many problem. The most of them, their mobility in the channel have a saturation and getting bad. So we should have to improve this mobility. So we use this strain engineering in the channel. And I'm going to talk about how we use the strain engineering technique. And the two parts of them, first is the substrate-based and process-based. And in the easy word, this is gonna be global strain engineering, and this is local strain engineering. And global and local is it have many difference. The global is we give the strain in the whole vapor. So the vapor has a fixed in the one characteristic strain. So this have a lot of problems. There is the problems, the expansive vapor, which means in the one characteristic vapor, and it make a little bit problem happen, it's gonna be trash. So the expensive and many defect, if we give the strain engineering, there is a little of the mismatch. It make a whole vapor is gone to trash. So this is the problem. And self-heating problem. When we give them the strain engineering, we use the IP process that have a lot of the heat. So there's a Summerbird's problem, and equally the dielectric is not a good heat control. So there has many problem because this reason. So one type of the strain is I said before. So the conclusion is the current time. This time we don't use the global strain at many, and this time we use the local strain because it have the we can give the strain engineering in the part of the vapor. So we can control the part to part or like a source or drain. So we can control at the same time and N channel and P channels MOSFET. This is very large advantage. So, and the much cheaper than global strain, and the threshold voltage shift is smaller because we can control the local to local. Mhm. So how we use the local strain? There's a first is we use the scissor. Scissor mean contact edge stop liner. It used the we gave strain engineering. We use this technique. You can see this figure. There's a like a source or drain. We add the source and drain point and regrowth the source and drain. When we And at the moment of the regrowth, the source and drain, what particle and what material we use, it make control the strain engineering. The the atom numbers is bigger, the material much bigger and heavier. So it can, when we use the bigger material in the source and drain, it's the same. It gives the channel in the compressive strain, and more lighter than the channel, we get the tensile stress in the channel. And this is the first thing. And this gonna be used. And this, look at this figure. It called the SMT, a stress memorization technique. We use the source and drain. We make it already, and we put the liner on the surface. And this liner give a source and drain a tensile or compressive strain. And then we're gonna hitting and annealing to the memorize this tensile and compressive strain. And then after the annealing, we shift off the liner. Then the source and drain have a memorization in the stress. So this is a much good technique, but we can think about the most 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 important thing about the summer budget. We should have to consider it. And this is the problem about the horizontal direction, and this is the vertical direction of the transistor. It means there's a gate and about the gate. Yeah. The transistor structure has a source, drain, and gate. The gate is a control of the channel. But when we scaling down to the gate, there's a gate only have to function as a controller, but the electron going to the gate, which means it's a leakage current. We use the gate stack as a SiO2 and the polysilicon because this advantage, this is good, but there when we going to scaling down, there have several problem here. First is the quantum tunneling, the direction tunneling, and polynodium tunneling. The direction tunneling is which mean is literally tunnel in through it to the dielectric because the dielectric thin is too much smaller. So the atom going through it. And the planar Nordium tunneling is a field assist tunneling. When we give to the positive voltage indicate, it make a energy band is much smaller. So the atom, the electron going to the leakage. So this problem is going up and going to bigger when we scaling down. So we should have to fix this problem. Look at this figure. The nano graph is the the thickness of the gate dielectric going to smaller. There have a no direction. There have a not a field assist tunneling. They give a weird direction tunneling happens, so it didn't match our theory. So we should have to fix it. Then the way of the we should have to fix this problem, we use the going up about the gate coupling. The gate coupling, it means is a gate that control the voltage of the channel. It improve this function, and we're gonna do this through the improve the dielectric material because the physically we can smaller is a limit about the thickness, so we can use the other material, so we improve the coupling. So high K material, what if this is the solution about this problem? So we use the high K material. And then this time it is over about the consumption. And thank you for listening.